Hello, pre-calculus students. Just want to make sure you understand the symmetries of the 6 trig functions by first, really, all you have to do is make sure you understand the symmetries of the cosine and the sine functions. So, remember our working definition of cosine and sine. Those are the x and y coordinates of a point p sub theta on the unit circle, assuming theta has been put into standard position. So you need to ignore that part of my math lab that refers to x and y coordinates. That's going to get in your way real soon. Okay, so stick with this definition. This is the working definition calculus students use. So, and remember, if theta is positive, we're talking about counterclockwise theta, and if theta is negative, if it's less than 0, then it is generated by going in a clockwise manner. All right, so what is the cosine of the opposite of theta compared with the cosine of theta? So here we have an angle theta. I'm taking theta to be positive here. Its opposite will be a negative angle, okay? But theta and the opposite of theta have the same magnitude, right? The absolute value of the opposite of theta is theta. So what that leads to are two triangles. There's O p sub theta, q sub theta, and there's O p sub minus theta, q sub minus theta. But I'm pointing to the same point, right? When you project up to the x-axis from p sub minus theta, that point at the foot of p sub minus theta at that right angle is the same q sub theta. And look at the coordinates of q sub theta. P sub theta by definition has coordinates cosine theta, sine theta. That's what we call its x and y coordinates. Those are our working definition of cosine and sine. If I've dropped a perpendicular down to the x-axis, then that x coordinate of p sub theta is exactly the x coordinate of q sub theta. Same way, if I go to p sub minus theta, I call its x and y coordinates cosine of that angle, which is the opposite of theta. Its y coordinate is the sine of the opposite of theta. But notice that p sub theta, q sub theta, and p sub minus theta are all on the same vertical line, right? So that's an argument for why the cosine of the opposite of theta is equal to the cosine of theta. Here's another argument. The triangles O p sub theta, q sub theta, and the triangle O p sub minus theta, q sub theta are congruent triangles. They share an angle theta. Remember, this angle as measured as part of a triangle is really the magnitude of it, theta. And they share a common side, O q sub theta. So therefore, they share this right angle at q sub theta and at q sub minus theta. So those triangles are congruent. And that leads us to say that the length of this side from p sub theta to q sub theta, which in the first quadrant can be taken as that exact coordinate, y coordinate, sine theta. That length there is the sine of theta. If these two triangles are congruent, that means the length from p sub minus theta to q sub theta, that length is also the sine of theta. The sine of theta is the length of that segment. P sub theta, q sub theta is the length of that segment, p sub minus theta to q sub theta. Okay, but p sub minus theta in this configuration is in quadrant 4. Positive first coordinate, negative second coordinate. The sine of the opposite of theta here is a negative number. All right, so the sine of the opposite of theta is equal to the opposite of the length of that segment. The length of that segment is the sine of theta. So therefore, in this drawing, where p sub theta is in quadrant 1, p sub minus theta is in quadrant 2, we have these two relations. Symmetry 1 is that the cosine of the opposite of the angle is the cosine of the angle. Those two x-coordinates are the same. Sine of the opposite of theta, which is the y-coordinate of p sub minus theta down here in quadrant 4, is the opposite of the sine of theta, y-coordinate of that p sub theta in quadrant 1. Okay, so that would be true of any angles that terminate in quadrants 1 and 4. You could do a similar argument for an angle theta that terminates in quadrant 2. Its opposite would terminate in quadrant 3, and so on. So we take as a rule for any theta that we have these two symmetries. The cosine is what we call an even function. You had that in college algebra. If you have the function of the opposite value is equal to just the function at the value, that's called an even function. Think of like y equal to x squared. Or you could have an odd function. These are very special symmetries. Think of the cubic. When you evaluate the function at the opposite of the value, it's the opposite of the function at the value. Think of the cubic function. Okay? Both the cosine and x squared are even function. Both the sine function and cubic function are odd functions. Just remember, most functions are neither odd nor even. However, now using what we know about the 4 trig functions, you can go through using their definitions. So for example, the tangent of anything is equal to the sine of that angle over the cosine of that angle by our definition of the tangent. Not the books, but the one that we've been talking about in these videos. Then you can see clearly this negative can come out front here using symmetry 2, this one here. Symmetry 1 has no negative sign coming out front. That one negative sign persists, so therefore the tangent of the opposite of an angle is equal to the opposite of the tangent of theta. You'll notice in all these there's only one other even function, the secant. That's the only one that only involves the cosine, which is nice and even. All the other trig functions involve the sine, and therefore we get one negative sign coming out. So the only two even trig functions are the cosine and the secant, and the others are all odd.